This video will help you go through the problems that you were given as practice problems for the Test 1 review. Feel free to fast forward to the parts that you need the most help with and the problems that you need to review more thoroughly. You were asked to write these in set builder notation, which basically is giving a formula that would generate the set you see here. And so what you're oftentimes looking for is see how the natural numbers are made use of, or even how integers are made use of in some respects as well. So for instance, in this one here, 1, 4, 9, 16, 25. Now this may take some people a little bit of time to recognize, but these are the perfect squares for 1, 2, 3, 4, 5. So it's 1 square, 2 square, and it keeps going on in that kind of pattern. So basically, if I want to, state that this in a different format instead of builder notation, I would say x equals elements of x such that x equals n squared, where n is a natural number. So that's one way of stating what this is. Others are a little bit less complicated. Because you can find an easy pattern to go by. For instance, this one here, each time I move from term to term, I'm moving up by 3. Now, the other thing we have to keep in mind here is that the previous one was an infinite set. This will keep going on forever and ever. This one is limited. It's finite. There's only 6 elements in it. So, for most times, situations like this, it's actually better to have it in roster notation, which is what this is. But if I want to make this in set builder notation, I want to try to find the pattern that'll let me see where the natural numbers come into play. So if I look at these values here, I can rewrite them as -4, which is the first term here, plus 3 times some number. That means the first one would be 3 times 0. -4 plus 3 times 1 would give me -1. -4 plus 3 times 2, which is -4 plus 6, would give me 2. So forth and so on, all the way up to -4 plus 3 times 5. Now, the natural numbers start at 1. So 0 is not a natural number, so I got to try to figure out a way of determining how I would, use the natural numbers. That's typically what's used for these kind of notations if I'm using set builder notation. So if n is supposed to be a natural number, then it seems as though, in the first position I have 0, the second position I had 1, and the third position I had 2. So it always seems like the number that I'm multiplying to the 3 is 1 less than the position number. So I'm going to say it's -4 plus 3 times n minus 1, and I'm going to simplify that a little bit, and it becomes 3n minus 7. So if I want to write this in a set builder notation, I would say that the set y are all elements y such that y equals 3n minus 7, and n is a natural number, and n is less than or equal to 6, or you can even say that n is less than 7, So there's different ways of writing it. There's a couple of variations you can have to this, but generally that's where you would have it. You can even have used this formula here and written the same kind of thing with that. This is just a more simplified version of this one here. On to the next problem. Now these are the exact opposite. This one, they're giving us set builder notation. They want us to write this in roster notation. The first thing I sometimes keep in mind is sometimes I have to make sure I know when I need to use ellipsis, which is those 3 dots that you can put at the end or at the beginning or both to indicate that there's a pattern that goes on forever in whatever direction it is. So we can see here that this is saying that M is the set of all elements x such that x is equal to n plus 8 and n is a natural number. So the natural numbers go on forever and ever and ever. So, so if I let n be a natural number, then my roster would be 1 plus 8, 2 plus 8, 3 plus 8, 4 plus 8, going on forever. And that's what these ellipses, that's what they're called, are. And so basically the roster would be 9, 10, 11, 12, etc., and so on forever and ever. So there is your roster notation for this, and it is an infinite set. This one, however, I have that Q is a set of all elements x such that x equals 6 times n is a natural number, and n is less than or equal to 7. So Q would be 6 times 1, 6 times 2, 6 times 3, all the way up to 6 times 7. Now, I used ellipses in here to kind of say there's a pattern going on here. And if I have an ellipsis that's in between, two elements, it just means that the pattern continues until I reach this point here. That's where it stops. Now, since it is a roster, I'm going to just list them all if I can. If it's a long list, I might use ellipses to kind of say, okay, you can get the idea of the pattern, and then, I'll put the ellipsis and then maybe the last 1 or 2 elements in there. But in the end, I'm going to have basically 7 items here, so it's not that long. So basically, I'm going to have 6, 12, 18, 24, 30, 36, and 42. And those are the numbers that appear in set Q in roster notation. On to the next problem. In this problem, you're asked 2 different questions to determine if it's true or false. That A is a proper subset of B, and B is a subset of A. Now, the difference between a proper subset and just a regular subset is that for a regular subset, the 2 sets could be equal. They could be the exact same, elements. Whereas for a proper subset, it has to be a situation where A has to have all elements that are in B, but it shouldn't have all the elements that are in B. It should, be a smaller set than B. So you shouldn't have the same number of elements, or, in A than B if you want to be a proper subset. Whereas for B to be a proper subset of A, B and A could be the exact same set, and it would work fine. So, now, they often will sometimes mix it up and give you, roster notation, set builder notation to kind of get the idea of what's going on. So, in order for you to do this, you need to know what these sets are so you can compare the 2. Now, in A, I have set A, which is given to us in this formula, which I'll get to in a moment. And I have B basically saying 1, 2, 3, 4, 5, 6, 7 with an ellipsis. So, in actuality, I could probably just said that B is the set of the natural numbers. But for me to compare A to B, I'm going to need to know what this ends up being. So basically, this is saying that, all elements in A are given by the formula 2n plus 1, where n's a natural numbers. So if I start mapping out what A is, it's 3, 5, 7, 9, so forth. So basically, it's the odd natural numbers starting at 3 for A, whereas B is basically all natural numbers. So obviously, even though these are both infinite sets, technically this is still going to have less numbers be part of it, because there are some numbers being excluded in A, whereas in B, they're included. So is A a proper subset of B? Well, A is definitely a subset of B. So that is true. Is B a subset of A? Well, B is actually bigger than A. It has more elements than A does. So there's some elements in B that are not contained in A. So B would not be any kind of subset of A. So it's true for the first statement, A being a proper subset of B, but it's false for the statement that B is a subset of A. For B, they're both written in set builder notation. Now this is saying that all the elements in A are given by the formula 2 times n, where n's a natural number. So since there's no ending there, basically we can see that this would go on forever. And same thing for B, it's going to go on forever, but instead of being multiplied by 2, the natural numbers are being multiplied by 4. So in roster notation, or roster form, A would be 2, 4, 6, 8, 10, 12, or basically all the numbers that are multiples of 2, whereas B is going to be the multiples of 4. Now, A has numbers in it like 2, 6, 10 that aren't elements in B. So A is not any kind of, A is not even a subset of B. So A cannot be a proper subset because A is not even a subset. B, on the other hand, all the numbers in B, all numbers that are divisible by 4 are divisible by 2. So all these numbers are going to be up here in set A. So B is a subset of A. It's actually a proper subset of A, but we're not asked that question here. So as far as, the columns go, A being I can say here that A is not a subset of B at all. So if A is not a subset, then A cannot be a proper subset. So that's going to be false. But B is a subset of A. That is true. For C, I have A being this roster, which are P, Q, R, S, T, all the way up through V, so they're in alphabetical order. Here, it takes a little bit of doing, but if you rearrange these in alphabetical order, you find out that they're the exact same set. So, is A subset of B? Well, A actually equals B. A is the same thing as B. So as a result, A would be a subset of B, but A is not a proper subset of B because they're the same size. They're the exact same set. B, however, would be a subset of A because B and A are the same size. It is a subset, but not a proper subset. So I have the same answer, but for totally different reasons than we did for B. In B, A was not even a subset of B. So, if it's not even a subset, it can't be a proper subset. But if it's a subset, it still has the possibility of not being a proper subset because it shouldn't be the same size. But B is a subset of A since they are in fact the same set. For D, we have B being the set 0, 7, 14, 21, 28. A is the set of all numbers that are basically multiples of 7 of the natural numbers. So A would be 7, 14, 21, 28, so forth and so on. B is 0, 7, 14, 21, 20. So basically, B is the exact same thing as A, except it also includes the number 0. That's really the only difference. B basically has one more term than A does. That's it. So is A subset of B? Yeah, it's a subset of B because, it has all the elements that are in A are also found in B. So it's a proper subset because it's not the same size. It's missing 0. Is B a subset of A? Well, no, because of that 0. 0 is not included in A, so B cannot be a subset of A, proper or otherwise. So it's true for the first statement and false for the second statement. On to the next question. There's different ways of handling problems like this. You can use Venn diagrams, but once you start getting beyond, 3 different sets of a universal set, it can get a little bit tricky to navigate, 4, 5, 6 circles and make sure they're all accurately placed and there's overlaps occurring correctly and things like that. So it's just probably best to focus your attention only on the sets that you need to worry about at a given time. So, for instance, with U being the universal set, which means that numbers 1 through, the integers or natural numbers 1 through 15 are the only elements we could possibly make use of here. If I want to find the union of X and Z, first I'm only going to focus my attention on those 2 sets. And a union means that I'm going to include all elements of these sets that belong to at least one of these 2. If it belongs to one or the other, it's going to be included. If it's a part of both sets, it's going to be included. So when I look at the numbers here, this starts with 4. This starts with 2. So 2, 3, 4 would be included. 5 would be included. 6 would be included. 7 and 8 is not in either one of these 2. So 9 would be included. 10 would not be included. 11 would be. 12 would be. 13 is not included. 14 would be since it's in both. And 15 would not be included. So this would be 2, 3, 4, 5, 6, 9, 11, 12, and 14. So for a union, I would include elements that belong to one of the sets, or the other set, or both. When I do B, when I do the intersection of V and Y, well, first I'm going to focus my attention on just V and Y. And I only want those elements that are contained in both. So the intersection means that it has to be in both only. If it's in one or the other, that's not good enough. It has to be in both. And so when I look at V, 1, 5, and 12 are the only numbers in there. The only number that's also contained in Y is 5. The 1 isn't, the 12 isn't. So basically this would be a set of one number, 5. When I look at the next one, C, the little apostrophe means that the members of the set that are not in X, or Y, or the union. So this means that I'm looking first, I'm not looking for what's in X. I need to know what's in X to deal with it. So I'm going to still focus my attention on sets X and Y. But I'm not going to use what's in X. I need this to figure out what's not in X. So for X apostrophe or not, or X prime, or the elements that are not in X, I'm just going to take the values that are in U that are not in X. And those would be 1, 5, 7, 8, 10, 12, and 13. So I'm looking at this set right here and Y. And again, I'm going to pick those that are in one or the other or both. So 1 is in this one, 2 is in neither, 3 is in this one, 4 is in neither, 5 is in both, 6 is in Y, 7 is in both, 8 is in this set, 9 is in neither, so it won't be included, 10's in both, 11's in Y, 12's in X prime, and 13's in both. So this would be the set 1, 3, 5, 6, 7, 8, 10, 11, 12, and 13. Now for D, when I do this cross multiplication, this means that I'm going to make ordered pairs of these two sets, which means I'm going to take elements from Z first. That's going to be my first element of the ordered pair, and elements in V for the second element of the ordered pair. So when I do Z and V, I'm going to focus my attention on this. So I'm going to have like 4, 1, 4, 5, 4, 12, 5, 1, 5, 5, 5, 12, and so forth and so on. So I'm looking for all possible ordered pairs Z, V, where these are elements that are in those sets. And this would be the entire list. So I'll pause a minute and let you read them. It's a longer list, and I'm not going to read through all of them, but you get the idea. Each of these numbers here are going to be paired with one of the three numbers that are here, making ordered pairs. So I'm going to have 1, 2, 3, 4, 5, 6. I'm going to have 18 ordered pairs as a result of this. For E, X minus Z, for set notation, this is the same thing as me saying X and not Z. So I'm focusing only on X and Z. Now I can either just say, okay, looking at X and excluding anything that also is found in Z. So I would say, okay, of this list here, 4 would be gone, 6 would be gone, 9 would be gone, and 14 would be gone. So what I'd be left with is basically 2, well, go back here. I'll be left with 2, 3, and 11, basically. I'm not going to remove a 12 because I don't have one to remove. But I can also look at it like this way, just okay, what's Z prime? So I'm going to look at any number in the universal set that's not in Z. And then if I do the intersection, I'm looking for numbers that are in both of these sets. So 2, 3, they're in there, and 11's in there. And that's it. 2, 3, and 11. So one way or the other, I can come up with that information. For F, I'm doing X intersects Z prime, which means I'm looking for elements that are not in the intersection of X and Z. So there's two ways I can actually handle this, and I'm going to kind of show you both. They both get to the same point. In method 1, I'm going to first find the intersection of X and Z. So I'm going to look at, X and Z and see, okay, what's in both of them. So the 4, the 6, the 9, and the 14 are both in X and Z. And then when I do the prime of that, the elements that are not in that, I'm just going to go to the universal set and name anything that's not in here. So basically, I would go to this universal set, get rid of the 4, get rid of the 6, get rid of the 9, and get rid of the 14. And I'd be left with this list here, 1, 2, 3, 5, 7, 8, 10, 11, 12, 13, 15. The second method is I can use De Morgan's law, which basically says if I do the negation of an intersection, it becomes each one of these negated, and it's going to become a union. So what I can do then is, okay, well, looking at these sets here, I mean, going back to, x prime is going to be all those numbers in here that aren't in x, and z prime is going to be all these numbers up here that aren't in z. And I come up with this list, and then I'm going to do a union of that. So anything that's in one or the other, but not either. So 1 would be included, 2, 3, 5 would be included, 7, 8, 9 would not be included because it's not part of either of the sets. 10 would be included, 11, 12, 13, 14 would not be included, and of course, 15. And I would end up with the exact same answer. So there's two ways to approach it. Yeah, both of them work. I mean, so it doesn't really matter which one you use as long as you're, making sure you're using it for the proper reasons. So whichever one you're more comfortable with. For the last one, you have basically all 4 sets being involved. So we have to make sure to do this, in, acceptable chunks here. And which means I want to do basically those that are not in X and those that are in Y, in a union with that with the intersection between Z and the elements not in V. So I got to figure out what X prime and V prime are. So X prime, which we made use of before, V prime is a longer list because it's basically all these numbers here excluding 1, 5, and 12. And so when I look at doing, okay, here, the intersection of X prime and Y, so I'm looking at these two sets and only those values that are in both. And so when I look at those, the 5's in both, 7's in both, 10's in both, and 13's in both. So 5, 7, 10, and 13 would be the intersection of not X and Y. I'm going to do a union with the elements that are in Z and those not in V. So again, when I look at these two sets, the Z and V naught, 4 is in both, 6 is in both, 9 is in both, and 14 is in both. So 4, 6, 9, and 14. And I'm going to do a union between these two, which means that, they don't have anything in common, but a union means is if it belongs to one, it's going to belong to the union. So 4, 5, 6, 7, 9, 10, 13, and 14 would be the union of those two, and that's what this set G would be. On to the next one. Pizza Hut has a special where you can order a pizza with any number of toppings for one low price. The toppings are mushrooms, pepperoni, extra cheese, peppers, bacon, hamburger meat, chicken, tomato, and spinach. How many different variations of toppings are there for ordering a pizza? And you have to show all work. And how many of these variations are proper subsets? Show all work. Now, part of showing the work may be just to give an explanation as well. But, essentially there's not a whole lot of work to show. It just, basically making sure that you know how to go about doing this. The first thing I'm going to look at here is that this list contains 9 toppings. And so basically based on the rules that you learned about, the number of different variations of toppings, basically they're asking for, the number of subsets that I could get from this group of toppings. So the number of variations being those number of subsets would be 2 to the 9th power, which is 512. Now, when I do this formula 2 to the 9th power, that includes even the instance where all the toppings are used. Now, if all the toppings are used, that's a subset, but not a proper subset. And so basically, I'd have to exclude that one instance where all the toppings are being used. So basically, that's one instance out of these 512 that I have. So the number of proper subsets would be 511. And that's all there is. So even though it says show all work in both parts, it's not a whole lot of work to show. And in B, it's probably more of an explanation than anything. For number 6, you're asked to create the truth tables for each one of these circumstances. So I'm going to kind of focus on each one individually and kind of lead us through it. Now, as I go through this, there's going to be truth tables being shown, and I'm going to show it using a couple of different ways that they showed in the textbook, just so that you know that there's a couple of acceptable methods just to make sure you're being clear. Typically, I will rewrite, I'll make longer truth tables so I can keep things in order, whereas the textbook will sometimes, just like kind of, intermingle things and then kind of label which was done first, second, third, fourth, so forth and so on. So if I focus on this first one, I'm doing basically the P, if and only if not Q. If that's true, then Q and not P is true, or something along those lines. That's basically what this is saying. If P occurs, if and only if not Q occurs, then Q and not P occurs. That's basically, that's how you would kind of read it. There's only two elements involved here, P and Q primarily. So I'm going to set up my truth table with every possible combination of P and Q's. Now, not P and not Q make their way into this, so I should definitely figure out what those are as well, so I have those included here as well. And all I'm doing here is negating P and negating Q. So anything that was true for P is going to be false for not P and vice versa. Same thing with not Q. And now what I want to do is start working on these. Now, I'm looking at P if and only if not Q. So I'm looking at this column here and this column here. And this is only going to be true if both of these are true at the same time or both of them are false. So they're both the same truth value. It's true. If they're opposite truth values, it's false. So here they're opposite truth values, so it would be false. Here they're the same truth value, so it's true. Here they're the same truth value, so it's true. Here they're opposite truth values, so it's false. So it's false, true, true, false. When I look at Q and not P, so I'm looking at these two inner columns, the AND indicates, the intersection here indicates that it's only going to be true when both are true at the same time. So in this third instance, it's going to be that this is going to be true. If for the rest, it's going to be false. So I'm going to have false, false, true, false. And so now since I have these two components, I want to do the entire thing now. I mean, I have this part, I have this part. I just want to do the if-then statement, the conditional statement. For a conditional to be true, either both of these have to be true, or this first instance has to be false. So really, the only time this is going to be false is if this is true and this is false. So in the second instance, this will be false, and all the others, it's going to be true. And this would be the truth table for that. For part B, again, I'm only really dealing with P and Q and their negations. So I'm just going to start with P and Q and, of course, come up with their negations because both not P and not Q are being used here. And so I want to look at the instance of P or not Q. So P, I'm looking at the two outer columns here, P or not Q. For this or statement, this disjunction, I'm looking for instances where at least one of them is true. If at least one is true, then this is going to be true. So in this instance here, this will be true, this will be true, this will be false, this will be true. So it's true, true, false, true. For this one here, I'm looking at the two blue columns. It's an or statement, same thing. If both are, the only time it's going to be false is if both of these are false at the same time. So the first instance is going to be false. The rest are going to be true. So now when I do their biconditional, which is what the symbol is here, a biconditional again is only true if both columns will have the same truth value. So these are opposite truth values, so it's false. These are the same truth value, so it's true. Opposite truth value, so it's false. Same truth value. If these are both false, if these have been both false, this would still be true. I mean, so I'm not looking to see like, they're both true. That's what makes them true. It's if they have the same truth value. That's what makes it true. So this one goes false, true, false, true. Now for this one here, I have P, Q, and R being mentioned. So I had to set up the truth table with those three variables to start off with. And the things I'm looking for, well, I need to figure out what the biconditional for P and Q is. So I'm looking at these two columns here. Now again, I'm looking to see where is the truth value the same. They're the same for the first two. They're opposites for the middle four. And they're the same truth value again, although false this time, for the last two. So it's going to go true, true, 4 falses, and then 2 more truths. Now I don't have to rewrite R because R happens to be this column here. So I have this component, I have this component right here. So I can go right to this overall statement. And since it's an OR statement or a disjunction, if at least one of them is true, then the whole thing's true. The only time it's going to be false is if both are false. So if you look here, I have both falses in the fourth line down and in the sixth line down. Everywhere else it should be true because it has at least one true for the rest of them. So it's going to go true, 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 false, true, false, true, true. And that's what the truth table is for that. Now for this one here again, you have P, Q, and R again, so I'm going to start off the table with those 3 values involved. And remember, these can get a little more complicated. There could be knots in there, there could be other conditionals and intersections. So keep in mind that, I mean, it could be more complicated than what these are showing. Because what I have to do now, I'm going to focus on Q or R. This disjunction here. And again, I'm looking for instances where at least one of these are true. That's what will make it true. If they're both false, that's when it's going to be false. So you can see here, it's only both false in the 4th line down and in the 8th line down. So this is going to be true, 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 false, true, 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 false. Now I'm going to focus my attention on the first column where P is and this column where the Q disjunction with R occurs. Because I want to figure out what this is. Now this is a conditional statement. So again, it's true as long as these are both true at the same time, or if P is false. The only time that this will be false is if this is true and this statement's false. So as I look at this, I have one instance here where it's true and then false. So this is the only instance where I'm going to have a false. The only other ones is that they're either both true or P is false. So I'm going to have basically the 4th line being false, all the other lines are going to be true. And that's what the truth table is. So as a quick recap, these are the truth tables that we came up with, excluding all the middle steps, but here are what they are. So double check with your work, see how they are. If you have any issues with these, make sure to go back and rewind this to look at how the truth tables were developed. But on to number 7. Number 7, you're given the statement, if it is summer, then it is hot, and you're asked to write the converse, inverse, and contrapositive of the statement. So basically, if I have a conditional statement, an if-then statement, the converse is simply switching the then part in the if part. So, instead of saying if it is summer, then it is hot, I'm going to say if it is hot, then it is summer. That's the converse. So it's kind of like an opposite statement. It's like kind of like, now the inverse is me negating both parts of the statement. So instead of saying if it is summer, I'm going to say if it is not summer, and I'm going to negate this part too, then it is not hot. So that's what the inverse would be. The contrapositive would be like me taking the converse and negating that. So I would say if it is not hot, then it is not summer. I could also look at the inverse as being, or the contrapositive as being the converse of the inverse. So there's 2 ways I can look at it. I could just say, say, okay, well then the contrapositive would be switching these if-then parts around, or that the contrapositive is basically the inverse of the converse. So it's either the converse of the inverse or the inverse of the converse. They both give you the same thing. So the contrapositive is if it is not hot, then it is not summer. And I have a little typo there. I'm not going to redo the whole thing because of it. I should say if it is not, if it is us not hot. That doesn't make any sense. Typo. I'm a math teacher. What do you expect? Number 8, same thing. You're given the statement: if a student spends at least 3 hours studying each day, then the student will pass. You're asked to write the converse, inverse, and contrapositive. So again, the converse is just switching the if part with the then part. So if a student passes, or if a student will pass, there's different ways to say it. They both kind of mean the same thing. If a student passes, then the student spends 3 hours studying each day. The inverse would be the negation of this original statement. So if a student does not spend 3 hours studying each day, then the student does not, and then the student does not pass. So does not. And then, of course, the contrapositive. If a student does not pass, then the student does not spend 3 hours studying each day. So it's basically negating this converse. So these are pretty straightforward. Just have to make sure you keep them straight and know which one's which. That's usually the biggest trick to it. For number 9, you're given this statement here. Assume that A and B are true and C is false. Determining if the following statements are true or false. So I still need to do a truth table, but I don't have to do a complete truth table. I mean, I have A, B, and C. There's three things here, and I mean, if I was doing that, I'd have to come up with those generally those 8 different options in order to test them out. But I'm only looking for the option where A and B are true and C is false. So that's the only instance I'm going to take into consideration. So I do a partial truth table here. And I'm still going to kind of do things the same way as I did before. So first off, I notice that I do have the negation of A in there. So I have not A right here. So I'm going to come up and say, okay, not A would be false. So I'd have that part being in here too. And I'm going to first do, okay, well, I'm going to do B or not A. So if B and not A are looked at, it's the disjunction. So as long as one is true, it's going to be true. So this part here is true. If A, then C. Well, I'm going to look at this, and if A, C, if I start with the true part for A, and it leads to this being false, that means that this is going to be false. So that's what I have here. Now, when I look at the final answer for this, and I'm kind of showing the other notation, when I put the biconditional in here, the only way a biconditional will be true is if these match the same. So if they were both true or both false, this would be true. Since they're opposite truth values, this would be a false statement. So overall, this would be false. So this is the other way you could possibly, show things on a truth table, is by showing. Now they would often say, okay, they would show like what you put in first. So I would say like, your textbook would do something along the lines of this. Say, okay, I did this first, I did this second, I did this third, and I did this fourth, to kind of keep track of how the logic kind of came up. The other stuff is given information. So for this one here, go start the same way. I mean, we're still starting with A and B being true, C being false. I'm going to need to know what the negation of C is. So I'm going to put that in there, and it should be the opposite of what C is, so it's true. I'm going to first do, so I'd put a 1 down here. I'm going to do not C and A. Well, not C and A would be I look at this and this, and if they're both true, then it's true, and that's what's going on here. And so I'd say, okay, well, this was the second thing I determined. The next one we'll look at is B or C, or B disjunction C. It's going to be true as long as one of these two are true, and B is true, so B or C is going to be true as a result. And so we'd say, okay, well, that's the third thing we figured out. And now I'm going to put the conjunction, well, not the conjunction, the conditional in. So the conditional is true as long as either, this is true and this is true, which is what's going on, or if this had been false. So when I do the conditional, That's also true as a result. And so the overall statement is, in fact, a true statement. And how do I put 3 here again? It should be 4. So there you go. Now for 10, you're asked to determine if the logical equivalence written below is true or false. If it is false, show how it could be edited to be true. So, in this first one here, you have a lot of things going on with this. I mean, these are pretty, a lot of operations are going on here. But I basically have 2 statements. I have this statement here and this statement here. For me to determine logical equivalence, I have to make sure that they have the exact same truth table. So I'm going to have to come up with truth tables for both of these and then compare the two. So I'm going to start off with P, Q, and R and come up with all the possible combinations of those. I'm going to focus my attention on this first one here, the left-hand side. So I'm going to work my way through this. So I'm first going to figure out, I know what happens with P. These are the true values for P. I got to figure out the true values for if Q, then R. And again, this is either going to be true if Q and R are both true, or if Q is given to be false. So as I make my list for that, if Q then R would be true for all the, it'll only be false for the second line and the 6th line. So now if I look at P or if Q then R, look at those two, then, again, if this is an or statement, as long as one of the statements are true, it's going to be true. So the only instance I have where they're both false is this one down here. So I'm going to have nothing but trues and a false right here. But that's not what I'm looking for here. I'm looking for the negation of that. So making some space there. So the negation of that is going to be, well, I'm going to take all of these and just do the opposite of them. So you're at this point right here. So all this work so far has been to figure out what's going on with the left-hand side. For the right-hand side, I have to now say, okay, well, on the right-hand side, I have the negation of P and I have the negation of R. So I have to start off like figuring out what those are. So, that's just me taking the true value for P and doing the opposite one. Same thing with the true value of R. I'm going to now figure out what if Q then not R is. So if Q then not R, Q and not R. So I'm looking at these two columns here. And again, it's only going to be true, or it's only going to be false, is if this Q is true and not R is false. So it's false here, true here, automatically true for anywhere Q is false. It's going to be false here, true, true, true. So that's we came up with that. And now I'm going to look at not P and this column here to get what the right-hand side is. And again, it's an and statement, so when I look at these two columns, it's only going to be true when both are true. It's going to be false otherwise. So as a result of that, this is what I get. So now to determine if this logical equivalence is true, I got to compare the left-hand side and right-hand side truth tables. So I'm comparing these sides here. And as I say, it start off, basically the same. They're both go false, 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 true. The difference is the last two statements. The last two statements for the left-hand side are false for those conditions, whereas the last two statements are true for this condition. So they do not have the same truth value or truth table, so they're false. Now comes the second part. How do I correct this to make it true? That's where it gets to be tricky. Now, what I'm about to show you is one possible answer. You could actually make some change. Now, it shouldn't change the entire way this thing looks, okay? Generally, you'd be looking to see if I could just change one of the symbols, or maybe move the parentheses, or change this arrow to maybe an or statement or an and statement or a biconditional statement, something like that. You're looking to see, what you can do to find the minimum number of changes, but there is sometimes going to be more than one possibility. So keep that in mind. So I know the statement's false. Now let's examine some things here. If I start with this statement here, the left-hand side, I want to see, okay, what are some equivalent statements? So one equivalent statement could be, by De Morgan's law, I could say, okay, if I do the negation of this conjunction, I would get basically the negation of the first term, that's a disjunction, this is a conjunction, and then the negation of the second term. So this could be written this way, which means I could have just possibly removed this and put this on the outside, and that would have been good. So De Morgan's law would also, so that would be a possible answer. This thing need to be moved. This would also be the case that, we have a rule here that, and there's different ways you can handle this, and I'm going to show both of them as I go through this. We also learned that, this conditional statement can be written as a disjunction. If Q, then R can be rewritten as not Q or R. These have the same truth values. So that comes from the conditional statement written as a disjunction. The reason why I have that here is because now if I use De Morgan's law again, I can negate this conjunction or this disjunction to make it a conjunction. I always get mixed up between conjunctions and disjunctions. I just want to say one or the other. So by De Morgan's law, I could, simply replace, this with this by De Morgan's law again. Now there's a way I can come directly from here to here because essentially I went through the steps where I would do the negation of a conditional statement written as a conjunction because there's actually a method for that too. So basically, and that's the one I focus my attention on here because this has everything written on the right-hand side exactly the same way, with the only exception is that where I had this originally, I now have this. So this one required, the fewest changes. If I look at this one up here, it's not a major thing either, but it's basically me, getting rid of what was here and putting something else out here. So that's actually could be considered by some to be two changes, or if you look at it as me just simply moving the symbol, you can look at it as one change. But I would accept either of those answers. So essentially, one way to do this is to basically make the statement true, is to change this conditional statement to a conjunction statement. So there you have that one. On to the next example. So same thing here. Show all work determine the logical equivalence if this is true or false or not. So very similar to the last one, except the only thing is the last one I had there, P, Q, and R. Here I have A, B, and C. But I'm going to start with the truth table. And I just mapped out every possible combination of true and falses with A, B, and C. I'm going to focus my attention on the right-hand side. So I'm going to start with the disjunction of B or C. And again, I look at B or C. As long as one of them is true, it's going to be true. So basically, any time it's going to be false is where I had both false, which are on line 4 and 8. So there's that. And so now when I want to do A and B or C, I'm looking at these two columns here. And for this to be true, then the truth value for both of these needs to be true. So both true, both true, both true, false. So basically I'm going to have 3 trues and the rest are going to be false. So now I'm going to focus my attention on the right-hand side. And as you see here, I have the negation of A, B, and C all involved here. So let me get those negations set up so I can make use of them. I'm going to look at first the negation of B and the negation of C. So I look at this in this column. Again, for this to be a true statement, both have to be true. So on line 4 and line 8, they're going to both be true. False everywhere else. And so now I'm going to do the negation of A with a disjunction with what we just calculated as this conjunction. So I'm going to do this here. So I'm looking at this column here and this column here. It's an OR statement, so as long as one of them is true, the whole thing's going to be true. So what I have here is false, 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 true, 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 true. And now I want to negate that whole thing because, you know, I have all this now. Now I have to finally negate that. And so if I negate that last column, I'm just going to basically take this one here and just do the opposite truth values. So I get true, 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 false, 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 false. And now when I compare the two columns, the left-hand side and right-hand side, I do see they do in fact have the same truth table. 3 truths followed by 5 falses. Therefore, this is a true statement. So sometimes it takes a good bit of work. It's a good bit of writing. It's not very difficult work, but you know, you have to make sure you're writing it clearly enough so you know which lines are which, and that you're leaving yourself enough space, and you can read your writing and things like that. So in this problem, you're given that 260 people were surveyed about their drinking preferences. And so you're told 180 like Coke, 80 like Pepsi, 70 like ginger ale, 40 like Pepsi and ginger ale, 28 like Coke and ginger ale, 31 like Coke and Pepsi, and 18 like all three. And then you're given some questions, the first of which you're asked to draw the Venn diagram, and then you're asked some specific questions about the number of people that, you know, like this or don't like that, or combinations and so forth. So the Venn diagram is, anytime you're asked questions regarding, you know, how many people like Coke but not Pepsi or ginger ale, you know, stuff like that, then you kind of know you need a Venn diagram. So usually makes it a lot easier to answer. So I'm going to set the Venn diagram. So I have my Coke circle, my Pepsi circle, my ginger ale circle. I have to be careful about how I fill this in, because if I look at some lines here, like I know 180 people like Coke. Well, you know, but those also include those that like Coke and ginger ale, those that like Coke and Pepsi, and those that like all three. Okay, so, you know, because I mean, I'm just saying, do you like Coke? Well, the people that are in this category, and this category do. And so some of the people might be counted twice. So I have to be careful that I don't do that. That's going to throw off my numbers potentially. So I like to try to start with the circumstance that, you know, is the most restrictive, and then kind of move my way out. So I'm going to start with the fact that I know that there's 18 that like all three. And that means that this region right here, where all three circles are overlapping each other, that's where those 18 people are placed. That means that with 31 like Coke and Pepsi, well, 31 is going to include those 18 that like all three, because these people like Coke and Pepsi. They also happen to like ginger ale too. So I'm going to take that 31 minus 18. That gives me a 13 here. So that's what's in this region here. I'm told that 28 like Coke and ginger ale. So I'm looking at this region right here. But remember again, 18 of those 28 like all three, so I'm not going to count them twice, which is why a 10 goes out there. And same thing for the 40 like Pepsi and ginger ale. That's in this region right here, but 18 of those 40 like all three, so I'm not going to count them again, which means I'm just going to have 22 out in that region. And so when I start working my way up again, okay, how many people like ginger ale? Well, 70 like ginger ale. Well, those 70 include those that have already been used up in these regions. So I got to subtract the sum of these numbers from 70, and that would give me 20 out here. And the same thing as I work my way up. There's Pepsi, there's 27. Now this entire circle should total 80, and when I get to Coke, this entire circle should total 180, and so that would be this here. And the last thing I have to make sure, because I mean, I have the universal set, because there's 260 people surveyed. Does that mean that all of them like these three drinks? Well, no, not necessarily the case. And if I basically take all these numbers that are in these circles, these are the people that like it, like one of these drinks or combinations, or there's 11 that don't like any of these drinks. So those have to be accounted for as well. They would be in the universal set, but not in one of these three regions. Now, with this information, I have enough to answer the questions that follow. The first question was, how many people don't like any of the three drinks? Which I kind of brought up as I was answering this question here, because I said, well, in this region of the three circles, these are the people that like, one or more of these drinks. These are the people that don't like it at all, so that's just an easy 11. How many people like only Coke? Now, when you like only Coke, that means I'm not including those that like Pepsi as well, or ginger ale, or all three of them. So I'm looking at this region right here. And I can see that's a pretty easy answer, because, I mean, the only number, I can see the number in there, it's 139. For D, how many people like Coke and Pepsi but not ginger ale? So I have this overlap here, this 31 that like Coke and Pepsi, but this 18 down here also like ginger ale, so I don't want to include those. So the region I'm looking at is right here, and that's going to be 13. How many people like exactly 2 of the drinks? So I don't want those that like only 1. I don't want those that like all 3. I just want these 3 regions here. And so that's going to be 10 plus 22 plus 13, which ends up being 45. How many people like Coke or Pepsi but not ginger ale? So with this Coke or Pepsi, that means they can like one or the other or both, but not ginger ale. So I'm looking at this region right here. It includes everyone that has a Coke or Pepsi, but it's excluding anyone that likes ginger ale. So that's going to be 139 plus 13 plus 27, which is 179 people. And the last question, how many people like at least one of the drinks? Well, I mean, there's a couple ways to handle this. I mean, that's basically, here's the 3 drinks. I mean, here's those that like just one. So basically anybody that falls within all these circles likes at least one of these drinks. So I can add up all these values, so I can look at, that's the region I'm looking at. But of course the easy way is to say, okay, well, again, going back, this is the number that like none. And that's the exact opposite of liking at least one. So if I just take 1 minus, or I'm looking for probabilities, if I take basically those that like none and subtract that from the total, that's going to give me the number of people that like at least one of them, or 249. Of course, if you add up all these numbers together, you're going to get 249 as well. So let's go on to the next one. So for this example, you have the Department of Foreign Languages of a liberal arts college conducted a survey of its recent graduates to determine the foreign language courses they had taken while undergraduates at the college. Of the 480 graduates, you had, and here's the information here. Now, the thing you have to keep in mind is they all have this term, at least 1 year of Spanish. So that means that they took at least 1 year of Spanish, which means that if there's anybody that doesn't fall in this group by that 480, they didn't have any language, any of these 3 languages at all. So I have to keep track of the fact that that might be the case. Much like the previous example, I'm going to start off with a Venn diagram. I'm going to let the blue circle represent those who had at least 1 year of Spanish. Green let for those that had 1 year of French and those that had at least 1 year of German. And of course, you can see that from the descriptions there's some overlap because there's some that had 2 of the languages or even 3. Now, I'm not going to go into as much detail to go through this, but if you kind of use the same kind of logic we used on the previous problem, you can work your way through it and get your information like this. And so these are the numbers that you would have in these various regions. So, so make sure, and again, I would start with the 3 here, work my way out. So when I had the 3 here, 18 that had French and German, well, that has to be a total of 18 in this overlap, which means that there's 15 out here. When I had 33 with Spanish and French, they had the total 30, so it's 30 out here, and so forth and so on. So when I get to like the 178 that had French, well, that's going to include these things that you've already calculated. So there's going to be 130 that are out in this region here. And of course, that leaves 34 out here that don't fall within the descriptions of any of these 3 circles. So, what does this mean? And you notice that you weren't asked to complete a Venn diagram for this, but to answer some of the questions that follow, like, for instance, how many of the graduates had at least 1 year of at least one of the 3 languages? So, I have to know what that means, and that basically means, okay, well, how many people fall within at least one of these 3 circles? So I'm looking for the total that's in this region here. Now, again, I could total up the numbers here, or I could realize that for a shortcut, I'm going to take the 34 who did not have at least 1 year of one of these 3 languages and subtract that from the 480. And that gives me a 446 of these students, these college graduates, that did not have at least 1 year of one of these 3 languages. For B, it says at least 1 year of exactly one of the 3 languages. Now, without a Venn diagram, that would be kind of hard to answer. However, they only want those who had only one, so none of the ones that had more than that 2 or more of them. So we're only looking at these 3 regions here. And I would total those up, 146, 130, and 101, and those would total 377. And of course for C, who had less than 1 year of any of these 3 languages? Well, either I could have at least 1 year of one of these 3 languages, or I would have to have less than a year. That's the exact. So basically, I'm looking for those who did not either take one of these courses or had less than a full year's worth of it. They may have dropped it or something like that, so they don't have the requirement for it. And so that's this region out here, which we of course can see easily as 34. So that's how you do this problem here. Let's go on to the last question at this time. So for this here, you're asked to, number 13, take the statements that you're given and determine if it represents a valid argument. And we're going to walk through the first one to kind of talk about, what makes a valid argument or not. So A, if Jenny studies, then she will be successful. If Jenny is successful, then she will have a good job. Therefore, if Jenny has a good job, then Jenny studies. Is this a logical argument? So as I start this off, I'm going to use some symbolism here. I'm going to let J stand for Jenny studies, S stands for Jenny is successful, and G, that Jenny has a good job. And so basically these 3 statements here, if Jenny studies, then she'll be successful is given that if J, then S. If Jenny is successful, then she will have a good job is if S, then G. And then therefore, which is this symbol here, if Jenny has a good job, G, then Jenny studies. So if G, then J. I want to see is, what I want to try to find out is if in each instance where both of these are true, does this also follow that this has to be true as well? So again, I'm going back to my truth tables. So I set up every possible combination of truth and falseness that these could have with each other. And I want to look at them and see, okay, does this follow as a standard reason? So I'm going to look at the first 2 columns here and check out to see, okay, if J, then S. Now again, for that conditional statement, either both of these have to be true or J has to be false. If it's the instance that this is true and this is false, it's a false statement. So based off of that, these are the truth values I get for if J, then S. And very similarly for if S, then G. Looking at these two columns again, if they're both true, it's true. If it's true for S and then false for G, it's false. If it's false for S, it doesn't matter what G is, it's going to be considered true. So these are the truth values for that. Then, of course, last I want to see, okay, well, what is the truth values for if G, then J? So I'm starting with this being my left-hand side, this being my right. So if they're both true, then it's true. If G is false, then it's going to be true. If G is true and J is false, that means that the statement's false. So these are the truth values I have for that. Now I have this truth table. Now how do I use it to determine if I have a logical argument? I'm going to look at the instances where both of these statements are true, and I want to look at the truth value for if G, then J. So there's 4 instances where both of these are true. As I check out the truth values for if G, then J, I can see that, well, I have 2 of them that are true, but these 2 down here in the middle here are false. Now, it only takes one of those to be false. If I have an instance where both of these conditions are upheld, yet this doesn't happen, this is not a true statement, which means it's not a valid argument. So, because here I do have at least one of these turning out to be false when both of these conditions are true, this is not a valid argument. It's not valid. For the next one, if I eat all night, then I will have a stomach cramp. I didn't have a stomach cramp, hence, I didn't eat all night. So, there's really only 2 things going on here. I eat all night is going to be E. I have a stomach cramp is going to be S. So the statements are, if I eat all night, then I'll have a stomach cramp. So if E, then S. I didn't have a stomach cramp, so I'm going to have not S. Hence, which is another word for therefore, I didn't eat all night, so I'm going to negate E. Does this stand to reason? So I'm looking at 2 main statements, E and S. So I set up the truth table with that. And first I'm going to look at, okay, well, if E, then S. So again, if E, then S, this will be true, this will be false, these 2 will be true because, the only time you're going to have false is if the E is true and the S is false. So this is what I get for the truth table for that. My next statement I'm assuming to be true is S is not true. I don't have a stomach cramp, so I'm going to have the negation of these. So that's going to go false, true, false, true. And then I'm going to do, okay, what's the truth table for not E? So I'm going to take this truth table here and just negate that. So, it's going to go false, false, true, true. So I want to look at any conditions where both of these are true at the same time. And I have only one instance of that right here. As I can see in that one instance, not E is also true. So that's all it takes. It's true. There's only one instance where both of these original statements are true, and the conclusion is also true. So this is a valid argument based off of the truth table we came up with. And for the last part of the last problem, if Howard is happy, then Robin is happy. If Robin is not happy, then Fred is happy. Fred is happy. Therefore, Howard is not happy. Is this a logical argument? So I'm going to let H, R, and S stand for each one of these people being happy. So when I make this statement using an Euler diagram, if Howard is happy, then Robin is happy. That's what this one is. If Robin is not happy, then Fred is happy. Fred, of course, is happy. Therefore, Howard is not happy. So, H, R, and F are the primary things I have here. So, I'm going to start the truth table with this in mind. So, I have H, R, and F. I'm going to go with the first statement. If H, then R. So, again, I'm looking, as long as the first statement is true, and the second statement's also true, so if H then R, they're both true, it's fine. If this is true and this is false, that would be false. And then, of course, any instance where H is false is going to automatically make the statement true. So the truth table is true, true, false, false, true, 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 true. For this one here, the second line, I need to first have not R. So I'm going to put that in there. So I'm just negating R. And now I'm going to say, okay, if not R, then F. So I'm looking at these two columns. So this would be true, this would be true, this would be true because they're both true. This would be false. True, 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 and false. So my truth table is true, 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 false, true, 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 false. Now I'm not going to rewrite F because we already have F over here. So I'm going to use that. It doesn't matter which order they go in, you know. I want to look for instances where these three columns here are going to be true eventually. But first I want to figure out, okay, where is Howard not happy? So I'm just going to negate all of these, and so I have these. So I'm going to look for instances where I have this, this, and this being true. So like this one here, and this one here. So there are three instances where all three of these are kept. And when I look at the results of Howard being not happy, I have two instances down here where it's true, but this one instance up here, it's false. You know, so that's all it takes, that one false, to make this an invalid argument, because it is possible for all these conditions to be met and this not being true. So this argument is also not valid. And that is the end of this video. If you have any further questions, please make sure to reach out and ask me about it. Until next time, have a good day.